Hello and welcome to today's class. Today we're going to be looking at thin cylinders again. So this is the second video in this series. In the first video we were looking at a pressurized thin cylinder and we looked at how we can calculate the hoop stress. We talked about the fact that there's three mutually perpendicular stresses: the hoop stress, the longitudinal stress and the radial stress. With thin cylinders, we can neglect the radial stress. So we're left with our hoop stress and our longitudinal stresses. We showed how you can calculate the hoop stress, PD over 2T, so based on the pressure and the diameter and the thickness of the cylinder. We showed how we could work out the longitudinal stress, PD over 40, so that our longitudinal stress is half what the hoop stress is. We then went on and had a look at changes in volumes. And in order to do that, we worked out changes in lengths and therefore strains in the hoop direction, diametral direction, diameter direction, and the longitudinal direction. And we showed that the volumetric strain is the sum of three mutually perpendicular strains. So we got to that point at the end of the last video. In today's video, we're going to be looking at a special case. We're going to be looking at spheres, and we'll show how the stresses on the skin of a sphere, or a pressurized sphere, are reduced in comparison to those on the skin of a pressurized cylinder. So that gives us some insight as to why you might store high pressure fluids in a sphere rather than a cylinder. So we'll have a look at spherical components, and then we'll move on and we'll have a look at joint efficiencies. Up until now, we've been talking very theoretically about structures. In reality, they will be possibly fabricated, they'll be manufactured in some way. So we'd have some sort of joint, whether that be a weld or a rivet or whatever. So we'll have a look at the influence of those on those nominal stresses that we've been calculating. Okay, so that's today's class, looking at spheres and then moving on and having a look at joint efficiencies. Okay, so let's have a look at a sphere and let's consider the stresses which are set up in the surface of that sphere in the same way that we did with the thin cylinder. So let's draw our sphere, let's cut it in half, let's draw a free body diagram, and let's consider the stresses that would be set up inside that sphere. Okay, so if we draw our sphere, look something like this. My sphere, chopped it in half. So we've cut through this position here. And let's consider this piece of material on the surface here. Now, with our cylinder, with our cylinder, we had hoop stresses and longitudinal stresses. So our hoop stresses are running around this direction. And remember, our longitudinal stresses were set up by the pressures on the end plates. Now, obviously, with a sphere, we don't have end plates. We have the same stresses in all directions. So we would also have hoop stress in this direction. Okay, because obviously with my original sphere, I could have chopped it in through in that direction. It would be exactly the same. So we'd have hoop stress in that direction. Okay. Now, my hoop stress is clearly going to be acting on this face. It's the stress which is set up in the cylinder to try and, in the sphere, to try and stop it expanding. Okay, so on this surface here, I would have hoop stresses. Okay. So you've got hoop stresses on all of those vectors there. Hoop stress. Let's put some dimensions on this. So again, let's call this diameter D. So B and thickness T. So let's work out how we can calculate what those hoop stresses are. Now, in order to do that, we're going to consider this free body diagram. We're going to consider it sat in equilibrium. It's in static equilibrium. So therefore, the forces inside the cylinder, which ultimately come from our pressure. I haven't drawn my pressure. We're pressurizing this. We've got pressure inside the cylinder. Let's draw that in a different color. We've got pressure on the inside of the cylinder. Okay, so if I were to look in this direction, I would see something like this. I would see my cylinder chopped. It has a thickness T. We've cut through this position here. And my hoop stresses are acting on that position there. And my pressure is acting internally on this projected face here. Okay, so we know pressure is force over area. So pressure equals force over area. So therefore, force equals pressure times by area. So the force going into the page here would be my internal pressure, P, times by this area of this circle, which is pi r squared. Pi r squared, the area of a circle, or P pi d over 2 squared, which is P pi d squared over 4. Okay, so that's the force going into the page here. We can also consider the force coming out of the page, the force resisting that, the force holding my sphere in equilibrium. That force comes from these stresses, these hoop stresses. Now we've said pressure is force over area, and also we also know stress is force over area. So therefore, my force equals my stress times by my area. My stress, this time we're calling my hoop stress. It's the stresses on these faces. And my area is my circumference times by my thickness. Given that this thickness is quite small, approximately that area there, so it would be the circumference times by the thickness. We could do this outside circle and subtract this inside circle to get an exact answer, but approximately it's the circumference, 2 pi r or pi d, pi d times by the thickness T. Okay, and then what we're going to do is we know this is sat in equilibrium, so we know the forces going into the page are the same as the forces coming out of the page. So we're going to equate this to this. Forces in both directions are equal. Okay, so we can simply say P pi d squared over 4 equals sigma h pi d t. Okay, so that d cancels with the second d there. That pi cancels with that pi. So what do we end up with? My hoop stress equals PD over 4T. So that's my hoop stress in my sphere, PD over 40. So this is my hoop stress for a sphere. Let's compare that to the hoop stress for a cylinder, okay, which is PD over 2T. That was my hoop stress for a cylinder. That's what we derived last time. So my hoop stresses in my sphere are half as big. We've divided by 4T this time instead of 2T. So my hoop stresses are half as big as my sphere as they are in my cylinder. And that helps us to explain why, if we were to look at a petrochemical plant or gas plant or whatever, if we're storing fluids at a low pressure, we can get away with using a cylinder. However, if we're storing storing fluids at a high pressure, we might want to consider using a sphere because the stresses set up in the surface of the structure are half as big. So we might want to consider using a sphere. Obviously, for economic reasons, we would prefer to use a cylinder. If we consider a cylinder, it might look something like this. We can store our fluid in our cylinder. Now, so the footprint of that cylinder on my site, on my plant, would be this. And we've got a certain volume inside that. So for a certain footprint on our plant, we've got a certain volume of fluid which we can store. If, however, we're storing fluid at a higher pressure, so we've opted for a sphere of the same diameter, because we've just worked out if we have a sphere, we're going to reduce the stresses in the structure. But in terms of volume to footprint, if this is the same footprint, clearly we can store less fluid. Okay, the volume of this is clearly going to be much greater than the volume of this. Okay, so in terms of volume to footprint ratio, this is much more economical compared to this. So we might, for economical reasons, want to store our fluid in a cylinder, but for structural reasons, we might say actually we need to reduce the stresses inside our cylinder or inside our structure. So therefore, instead of opting for a cylinder, we're going to opt for a sphere so that we can halve those stresses. Just as we've seen on the previous page there, our stresses, our hoop stresses have been halved in a sphere compared to a cylinder. In the last video, we discussed why we might want to consider changes in volume. Okay, we did that last time for a cylinder. We're going to now look at that for a sphere. So we've looked at the hoop stresses. We've shown that the hoop stresses are half in a sphere compared to a cylinder. Let's now have a look at the change in volume. Okay, and last time I introduced this term volumetric strain. Okay, so our change in volume equals our original volume times by our volumetric strain. And we also showed that our volumetric strain was the sum of three mutually, let me spell that correctly, mutually perpendicular strains. Remember, we derived that last time with Cartesian coordinates, this idea of having a cube, and we then pressurized it so that it's changed shape, changed into something like this. So my strain was there, and we added those three bits together. Remember, we added the strip on the side, the strip on the top, and the strip on the back. Okay, so we showed with Cartesian coordinates how our volumetric strain was the sum of our three mutually perpendicular strains. And we then said, well, if we know that for Cartesian coordinates, we can then look at that for polar coordinates. And with our cylinder, our three mutually perpendicular strains were the longitudinal strain, the strain in this direction, and the diametral strain plus the diametral strain. So we had two lots of diametral strain, one lot of longitudinal strain. We added those three mutually perpendicular strains together to get the volumetric strain for our cylinder. This time, however, when we consider our sphere, our three mutually perpendicular strains, well, we've got the hoop direction, diametral direction, which is the same as the hoop direction. Remember, we showed that the diametral strain was the same as the hoop strain. So we've got the hoop strain in this direction. We've got the hoop strain in this direction. And obviously we'd have hoop strain coming into and out of the page, hoop strain. So our three mutually perpendicular strains are going to be 3 times the hoop strain. Okay, 3 times the diametral strain, which is the same as 3 times the hoop strain. So our three mutually perpendicular strains would be 3 lots of the diametral strain, which is equal to 3 lots of the hoop strain. Okay, remember we showed that last time the diametral strain was the same as the hoop strain. Now, our hoop strain, again, if we look at the previous video, we've got our hoop strain. It's 3 times by 1 over E, lots of my hoop stress minus Poisson's ratio as well the hoop stress. Okay, remember we showed this last time that actually the strain was the sum of 2 components for our cylinder. It was our stress over Young's modulus is strain, so the strain is made up of 2 components, the strain in the hoop caused by the hoop stress and the strain caused by the longitudinal stress. But this time, because we're dealing with a cylinder, a sphere rather than a cylinder, we don't have longitudinal strain here, we have hoop strain. We've got hoop strains in 2 different directions. Okay, so again, my strain is made up of 2 components, the strain caused by the hoop stress in this direction and the strain caused by the hoop stress in this direction. So we've got 2 lots of our hoop strain. Okay, clearly we can factorize that. So that's 3 sigma h over E, lots of 1 minus Poisson's ratio. My hoop strain we've just calculated, so 3 over E. My hoop strain, remember in our previous slide, my hoop strain PD over 40. Okay, so let's plug that in. So we've got PD over 40, 1 minus Poisson's ratio. So that's our volumetric strain for our sphere. So if we're interested in the change in volume, which we could be, so particularly if we're selling our product by volume, our change in volume because we've pressurized this sphere would be our volumetric strain. So that's 3 PD over 4 TE, lots of 1 minus Poisson's ratio times by the original volume. If we multiply that by the original volume, there's my volumetric strain. Okay, so last time we worked out our volumetric, our change in volume. Last time we worked out our change in volume for a cylinder. Now we've got our change in volume for our sphere. So up until now, we've been considering the nominal stresses which are set up in our thin cylinder or our thin sphere we've shown that the hoop stresses in our thin cylinder are PD over 2T, and the hoop stresses set up in our sphere are 2T, PD over 4T. They're half as big. Those are our nominal values, and they're based on the pressure and the diameter of the sphere or the cylinder, assuming it's a perfect structure, assuming there's no stress concentrations, assuming there's no defects inside our structure. In reality, obviously, that structure needs to be manufactured in some way. If we consider a sphere, a cylinder, we look at our cylinder, like something like this. We've assumed it has a certain thickness. And up until now, we've been considering just the diameter and the thickness of that cylinder so that we can work out the hoop stresses which are set up inside that cylinder. Now, in reality, obviously, that's manufactured, and you might manufacture that by rolling a piece of sheet and then riveting it together, for example. So down here, we'd have a series of rivets or a seam weld or whatever. In some way, we've manufactured this structure. So those nominal stresses are going to be influenced by how good those joints are, the efficiency of those joints, and we must take that into account. Now, how do we do that? Well, we simply take our nominal stresses and multiply them by an efficiency factor. So if we look at our cylinder, our hoop stresses, PD over 2T. However, those hoop stresses, remember, there's my material, my piece of material, my hoop stresses are going in this direction. So my hoop stresses and my longitudinal stresses are going in this direction. Okay. So the hoop stresses are trying to stop the cylinder from expanding. The longitudinal stresses have been set up by the pressures on the end plates of our structure. Now, looking at that, the hoop stresses go over this joint. Okay, the longitudinal joint there, the efficiency of that influences the hoop stress. Okay, so all we do is we add the efficiency of the longitudinal joint there. Okay, so my hoop stress is influenced by the efficiency of the longitudinal joint. Now, initially that's counterintuitive, that we take our hoop stress and that has the efficiency of the longitudinal joint. But when you look at this diagram, you can clearly see the hoop stresses are going to be going over the longitudinal joint. If we were to manufacture this structure, it's a very long structure, we might also need to have some sort of joint here. So we're joining sheets in that direction as well. And clearly we can see there now the longitudinal stresses are going to be going over the hoop joints. Okay, so the longitudinal stresses are simply PD over 40. That was the nominal stress. And then we put on there the efficiency of the circumferential joint or the hoop joint, okay, which is around here. Okay, now these numbers between their efficiencies, so they'll be between 0 and 1. They're based on historically on empirical data, so testing, experiments, previous knowledge and experience. You might say, okay, depending on a weld, it might be 0.5 or 0.6, depending on a rivet, it might be whatever. Historically, that's based on empirical data. You'll be given those numbers. Okay. More recently, those numbers are established via things like finite element analysis. We can start to use computational tools to understand what those joint efficiencies are. But all we need to consider is that those nominal stresses are influenced by those joint efficiencies. Okay, those are for my cylinders. Now, obviously, for my sphere, as we've seen today, we just need to consider the hoop stress. There's no longitudinal stress to consider, but the hoop stress is half what the hoop stress in the cylinder is, PD over 40. And the efficiency, we don't need to consider longitudinal joints or hoop joints, circumferential joints. We just need to consider the efficiency of the joint. Okay, there's no distinction between the directions. All directions are the same, obviously, with our sphere. So we need to consider the efficiency of the joint there. Okay, so there's our structure. There's our manufacturing our structure. Our longitudinal stresses go over the circumferential joint. The hoop stresses go over the longitudinal joint. And we just take those nominal stresses and we add a efficiency factor, either a longitudinal joint, circumferential joint, or if it's a sphere, the joint. And I say those values will either be established empirically through testing and experience, or through computational tools, through simulation and finite element analysis. Okay, so we've shown that our hoop stresses are twice as big as our longitudinal stresses when we're dealing with a pressurized cylinder. So let's consider a good example, a simple example, which you guys are all aware of, where we can clearly see that our hoop stresses are bigger than our longitudinal stresses. So what do we notice about that? The hoop stresses are twice as big as the longitudinal stresses. The hoop stresses have got 2 on the bottom, the longitudinal stresses have got 4 on the bottom. So the hoop stresses are twice as big as the longitudinal stresses. Now, you guys know that if you're cooking sausages on a Sunday morning for a fry up, how do they split? What direction do they split in? Well, they split longitudinally due to the fact that the hoop stresses are greater. So let's consider a cylinder, a sausage. We're cooking that, so we're putting some pressure on the inside. It's gases expanding internally, and if we don't pierce those sausages, what do? They split in this direction. Now, the reason that they split in that direction is that the stresses in this direction are twice as big as the stresses in this direction. Okay, we've just said now the hoop stresses are PD over 2T, and the longitudinal stresses are PD over 4T. Okay, so the hoop stresses, the stresses in this direction, are twice as big. Okay, so the gases internally within the sausage are expanding, and the hoop stresses are twice as big as the longitudinal stresses acting in this direction. The hoop stresses are twice as big, and that rips open the skin of the sausage in this direction. So we get our split in our sausage running like that because our stresses are twice as big in that orientation. So that's quite a nice visual application that everybody is aware of, which clearly shows that our hoop stresses are bigger than our longitudinal stresses because of the orientation of this failure. So if we go back and recap what we've covered in this class, we've been thinking about pressures which are contained within a structure and the stresses which are set up within that structure. We've shown for a thin cylinder, we get 3 mutually perpendicular stresses. The hoop stresses caused by trying to expand the cylinder, and the longitudinal stresses caused by the pressures on the ends of the cylinder. There are also radial stresses which would be mutually perpendicular to those 2 directions, but as long as our diameter to our thickness is below a certain value, about 1 in 20, we can neglect that. They can be assumed to be constant, and they can be assumed to be insignificant compared to our longitudinal stresses and our hoop stresses. So for our pressurized cylinder, we showed that our hoop stresses were PD over 2T, and the longitudinal stresses PD over 4T. And we did that by considering free body diagrams, taking our sphere, chopping it in half, looking at it sat in equilibrium, and we can work out what the hoop stresses are and the longitudinal stresses are. And the big take home was this: the fact that the hoop stress is twice the longitudinal stress. The change in length of the cylinder, we showed how we can calculate that. That led us to the strain in the longitudinal direction. The change in diameter, we could work out that. We showed that the hoop strain was the same as the diametral strain. And then from there, we could say, okay, well, the change in diameter, we've got the change in diameter, we've got the change in length. We can work out from those three mutually perpendicular strains, 2 lots of the change in diameter and 1 lot of the longitudinal strain. We can work out the change in internal volume. So this is what we showed at the end of the last class. We then went on and we showed that our thin sphere, in today's class, we've been talking about the special case of a sphere. We showed that the hoop stresses are halved by using a sphere rather than a cylinder. And we then went on and showed how we can calculate the change in internal volume. And then finally, we've had a look at the joint efficiencies. This idea that we've been considering the hoop stresses and the longitudinal stresses in our cylinder or our sphere as nominal values. We haven't been considering the manufacturing at all. But if you consider manufacturing, you must consider the efficiency of the longitudinal joint when you're considering the hoop stress. You must consider the efficiency of the circumferential joint when you're dealing with the longitudinal stresses. And with our sphere, we must consider obviously the efficiency of the joint when we're considering our hoop stress, the stress on the surface of the cylinder. At the end of that handout, there are 3 more examples. Have a go at those. I'll upload the solutions to those so that you can try those. We'll also discuss the content of this video and the examples, and we can go through any questions that you've got about any of that in class. Okay, so have a look at those examples and we'll cover that next time. But that really brings to a close the thin cylinder theory. If you've got any questions on that, please let me know, and we'll take it from there. Until then, until next time, I'll see you later. Thank you. Bye-bye.